In this lecture, we shall consider finding the shear force and bending moment values for the case of a simply supported beam with an eccentric or unsymmetric point load. Let's draw a simply supported beam with one end hinged and the other end with roller support. Let's label it as AB. We also mark a key point C such that it is eccentrically or unsymmetrically placed over the beam with respect to the midpoint. We show a point load of P kilonewtons acting over it. We now label the lengths of the parts of the beam created by the point C as A and B meters and the overall length as L meters as well. We drop down the projections from the key points as usual and draw zero datum lines for the shear force and bending moment diagrams. An arrow pointing towards the right is shown at the end A, representing the reference from which the length of an imaginary cross-section is measured and is marked as variable x. Now, before proceeding with the method of sections to find the unknown resistive forces and moments at various sections, we first need to find the reactions Ra and Rb at the supports. Let's assume tentatively that these are pointing upwards. To solve for these two unknowns, we need at least two equations mathematically. Considering static equilibrium of the entire beam, we get the two equations by balancing the beam vertically and also balancing the moments about some known point, say point A. The first equation states that the summation of the forces along the vertical y direction is 0, giving Ra plus Rb equals P kilonewtons. Let's number the equation as 1 for later reference. The second equation states that the summation of moments active and reactive is 0 about the point A, giving Rb as P times A over L. From equation 1, we obtain and simplify the value of Ra as P times B over L. Henceforth, we may directly write the reaction value at some support of a simply supported beam due to an acting point load as simply the point load times the ratio of distance of the load from the other support over the overall length L, without the need to perform initial calculations for minimizing our time and effort. Now let's write the shear force equations for respective parts of the beam. For region AC with x varying from values 0 to A meters, shear force at x equals plus Ra, which is plus P times B over L kilonewtons and is a constant. For region CB with x varying from values A to L meters, shear force at x equals plus P times B over L minus P. This is simplified further to get minus P times A over L, which is also a constant value. The bending moment at x for region AC is written as plus P times B over L times x, which varies linearly over the length. For region CB, bending moment at x equals plus P times B over L times x minus P times x minus A, which can be simplified further as shown, and equals P times A times 1 minus x over L and is found to be linear with respect to x. We apply the limits of the range of values of x to the equations for these regions and plot the values in the shear force and bending moment diagrams. The shear force is seen to vary from a constant value of plus P times B over L kilonewtons for the first part separated by the point load to another constant value of minus P times A over L for the latter part. The bending moment is seen to vary linearly from zero values at the support ends to reach a maximum value of plus P times A times B over L kilonewton meter, indicating a sagging moment that tries to bend the beam downwards. In the next lecture, we consider analyzing the shear force and bending moment values for the case of a simply supported beam with a uniformly distributed load over the entire length.